talk about angular speed, also known as angular velocity. The basic idea of angular speed is how much is an object rotating per unit of time. So you can compare that to regular speed, where you think about how far does an object travel per unit of time, some unit of distance per unit of time. Here we're thinking this object is rotating. We don't care how fast it's going in an absolute sense, but just how much it's rotating per unit of time. So the formula for this, the symbols are a little confusing, but let's just break this down. So omega, so that's omega, that's often the symbol used to denote angular speed or angular velocity. Theta, that is the angle that an object rotates. So that's the angle of rotation. And t is just the amount of time to make that rotation. So this is similar to the formula for regular old velocity, sometimes called linear velocity, in that, but instead of distance divided by time, it's the amount of rotation divided by time. So that may help you remember how angular velocity is defined. But in a more practical sense, let's look at some problems. Okay, if a Ferris wheel makes one full rotation every 4 minutes, what is its angular velocity in radians per minute? So let's just think about our formula, and then we'll see what we can do here. So we have omega, that's the angular velocity. It should be the angle of rotation divided by time. Well, what is the angle of rotation? How much is one full rotation, right? That's how much of an angle it goes through every 4 minutes. So one full rotation, that's 2 pi radians, right? 2 pi radians. And the amount of time it took was 4 minutes. So we have 4 minutes in the denominator. And you'll notice that this has the right units, right? It's radians per minute, radians over minute. So once we cancel this, we get approximately 1.6 radians per minute. So again, it's very important that you pay attention to the units that you're asked for. Sometimes you'll be asked for radians per minute. You might also be asked for revolutions per minute. A revolution and a rotation are the same thing. So you just have to pay attention to what the unit they ask for is and make sure you answer the right question. But the rest of it is mostly about converting between these different units. So converting between radians and revolutions, but it's all based on this idea that 2 pi radians is the same as 1 revolution. So let's look at another question. If a record spins at 76 revolutions per minute, what is its angular velocity in radians per second? Well, we're told 76 revolutions per minute. Let's just start with that. So 76 revolutions per minute. And we want to know radians per second. So what we can do here is just think about unit conversion. We want to convert revolutions into radians. And we know that, let's just mention over here on the side, remember that 2 pi radians is equal to 1 revolution. And with that, we can make a unit conversion factor which will give us the answer. So because we want to know the number of radians per second, we'll put in 2 pi radians divided by 1 revolution. We put the revolution in the denominator so that it will cancel with revolutions in the numerator and leave us with radians per minute. But remember, we were asked for radians per second, and so we need to do one more conversion. We need to multiply by 1 minute divided by 60 seconds, because there's 60 seconds in a minute. And this will cancel the minutes, the revolutions, and leave us with radians per second. And when you multiply this out, you get that this is approximately 8.0 radians per second. All right, now if we're told that a wheel spins at 6 radians per second, we want to know how many revolutions per minute does it make. Well, we're told 6 radians per second, and to get that into revolutions per minute, well, let's start by converting radians to revolutions. So we'll take the factor 1 revolution divided by 2 pi radians. And be careful, it's easy to make the mistake of getting this fraction backwards. But as long as you include the units, you'll be sure to notice that the radians will cancel in the right way and leave you with revolutions in the numerator, which is what you want, revolutions per minute. So just be careful to always include your units so that you know that the units are canceling in the right way. Okay, so now we have, once the radians will cancel, that'll leave us with revolutions per second, but we want revolutions per minute. So we just have to get minutes in the denominator. So we'll take 60 seconds over 1 minute, right? 60 seconds equals 1 minute. And now the seconds in the numerator will cancel with the seconds over here and leave us with revolution per minute, which is what we want. And now, when we multiply all of this out, we get that this is approximately 57 revolutions per minute. All right, a wheel spins at 12 radians per minute. How many revolutions per hour does it make? Well, let's start with what we're told, 12 radians per minute. And what do we want? We want revolutions, so we have to convert radians to revolutions, and we want hours, so we want to convert minutes to hours. So let's start with radians. We're going to take 1 revolution for every 2 pi radians. And that's the right way to do this because we want the radians to cancel and leave us with revolutions in the numerator. And then we need to get hours in the denominator. We want revolutions per hour. And so we need to cancel minutes in the numerator. We want 60 minutes is equal to 1 hour. And so now the minutes will cancel. And now we have revolutions per hour, and we just need to multiply all of that out. And this comes out to be approximately 115 revolutions per hour. Now last, let's talk about relating angular and linear speed. So remember, angular speed is just how fast is a wheel rotating, or some sort of circular object, how fast is it rotating. And linear speed is how fast is an object on the perimeter of that circle, how fast is it actually traveling. Another way to think about it is if you had a wheel, how fast would that wheel be going as it rolls along the street? So the key here is that 1 revolution of a wheel is equal to 2 pi times the radius of the wheel. So that's r, that's the radius of the circle. right? So for every one full revolution that a wheel makes, it's gone 2 pi r. That's the amount of distance that it would have rolled. So with that extra conversion factor, we can take an angular speed and convert it to linear speed and vice versa. Let's just look at a quick example. If a wheel of radius 14 inches makes 4 revolutions per minute, what is its linear speed? So in other words, again, we have a wheel that's sort of rolling down the street at 4 revolutions per minute. How fast is it rolling down the street? So all we need to do is take 4 revolutions per minute. And again, 1 revolution is equal to 2 pi r. So we want to cancel out that revolutions and give us a linear distance. We want so we want to multiply by 2 pi r inches over 1 revolution. Again, because 1 full revolution and the wheel will have gone 2 pi r inches. And since r is 14 here, we can just rewrite this as 4 revolutions per minute times 14 times 2 pi is 28 pi inches per 1 revolution. So now the revolutions cancel, and we're left with inches per minute. This comes out to be about 88 inches per minute. And if we wanted a slightly more useful unit, because inches are kind of hard to visualize, we could convert to feet by just taking 1 foot divided by 12 inches. Right now the inches will cancel and give us feet per minute. And so 88 divided by 12, that comes out to be about 7.3 feet per minute. So that's the speed that the wheel would be rolling down the street if it was revolving at 4 revolutions per minute.